we are doing in our group by selecting a few specific examples of high commercial importance. And in the second part, I will focus on only one topic and then I go a little bit deep into the characterization and other issues related to catalyst performance to derive structure activity correlations. So I have used a kind of guiding system. So part 1 and 2. So that you can easily trace the status of my presentation. So let us start with the first topic of part 1. So that is oxidation of cyclohexane to adipic acid. So this is the commercial process for adipic acid synthesis, which has a huge market, roughly 4 million tons of adipic acid produced worldwide every year. So you may ask, when this process is known and is running on a industrial scale, why do you want to do it again? What is new? Is it a kind of repetition? I said no. Our approach is somewhat different from the existing process. I will show you the novelty of our approach in the next slide, but before going to show that, I will tell you the disadvantages associated with this process. If you look at this process, this involves two steps, step 1 and step 2. In the first step, cyclohexane is converted into cyclohexanone and cyclohexanol. So one is ketone, one is alcohol. So this is popularly known as KAI mixture. And in the second step, this KAI is oxidized to adipic acid. If you carefully observe, the first step, the conversion is less than 5%. So less than 5% conversion means 95% of unreacted cyclohexane has to be recycled. Recycling is not free. It incurs some additional costs. This is the first disadvantage. And also it runs at high pressures, 10 to 20 bar. So it's better to do it at ambient temperature if possible. And the second step, using nitric acid, means production of some certain amounts of NOx. From environmental point of view, this is not eco-friendly reaction. So it's better to have an alternative. But still it is running on a commercial scale because there is no option at the moment. So people have also tried to produce adipic acid from other substrates, but still is a two-step process. Same process. And various other research groups have also tried from different other sources, but the results achieved have not reached commercial scale. So the novelty of our approach is that we would like to produce adipic acid in one step, directly from cyclohexane to adipic acid, either by minimizing the KI or to get adipic acid. This is only exploratory research to look for the possibility of producing this. I will show you is it possible or not in the next coming slides. So we have used gold nanoparticles to do this reaction. So before going to show that, if you look at the applications of adipic acid used has variety of applications. It goes to polyamides, polyurethanes, esters, and plasticizers. I'm not going to read everything, but what I want to say is that adipic acid is very important chemical in our everyday life. And if you look at the adipic acid production statistics and consumption statistics and growth rates, so in the last year, adipic acid produced about 4 million tons. And the major producers are United States, followed by Western Europe, and then goes to Asia. If you look at the growth rate, the average annual growth rate is at the moment is 3%, which is expected to increase even by 8% in the next 5 years. And the growth is more in case of Asia Pacific, followed by Middle East and Australia. Some new plants are also coming up from ExxonMobil, Sinopec, and Aramco industries. So now I will show you our results. So we have prepared gold nanoparticles, supported gold nanoparticles using various supports. I am showing here only the two supports because titanium and alumina has shown the formation of the smallest nanoparticles. If you look at the histogram here, it is blurred, I know. The particles that are formed on titanium support are varying the range from 1 to 2 nanometers, maximum 3 nanometers. And then, if you look at the alumina, they are 2 to 4 nanometers. And we have also used other supports where we have 5 nanometers, 10, 20, up to 20. They are not that active and selective. So if you can also see nice crystal planes, but it's blurred now. So if you zoom this area, you can also calculate this interlayer distance of 0.23 that corresponds well to gold 111 crystal plane, and in case of alumina, it is 0.14 nanometer, which is characteristic of gold 220 crystal plane. So we have also tried different other supports. Mainly we have used 2 basic supports, calcium and magnesium, 2 reducible supports, zirconia and titania, and 1 non-reducible support. In addition, we also use different oxyfluorides and metal fluorides, but we got the best results from TiO2. So this is the activity. This figure looks somewhat complex. I'm sorry for that, but just consider the first 2 rows. The first blue one is conversion of cyclohexane, XCH, CH is cyclohexane. And second row green one is selectivity of adipic acid. So if you look at this among different supports, so titanium has shown the relatively good performance. And other products are again cyclohexanol and cyclohexanone, which we are not able to prevent. But still, until now, to our knowledge, there is not even single source of publication where adipic acid produced in one step directly from cyclohexane. We are the first to claim this formation of adipic acid in one step from cyclohexane. The conversion selectively achieved roughly 26 and 26%, which is not really very high for commercialization, but this is the first knowledge on this approach. So we just show the possibility that it is possible. In the future, probably it might go further. So after this monometal catalyst, we thought, okay, how to improve adipic acid selectivity at acceptably high conversion. So we tried to dope second metal to this, and we have used silver and we have used palladium in the same concentration like gold, 1% each. When we add silver, the selectivity of cyclohexanone is increasing, the black one. But when we add palladium, adipic acid is increasing, but not to the extent we want. But there is some improvement. What we learned from this study is that the second metallic component has some influence, and both are behaving differently. Silver improved the selectivity of cyclohexanone, and palladium enhanced the selectivity of adipic acid. Then we are also curious to know why TiO2 is the best compared to other supports. Is it only the particle size or something else is also responsible for this? To check that, we also done, I made a diagram here, particle size versus X is the conversion, S is selectivity. Selectivity of KAI, selectivity of adipic acid, and the conversion. So you can see that smaller the particle, better the performance. So in addition to particle size, we also used XPS to estimate the surface composition and compared between all 5 supports. So you can also see that gold to metal ratio is high in case of titanium compared to other supports. That means there is an enrichment of gold on the surface. And then we also calculate the dispersion and the active metal area of gold. It's not the total beat area, it's the active metal area of gold. These are also high in case of titanium. So it is quite convincing that good correlation between particle size, gold enrichment, dispersion, and catalytic activity is obtained. Hope you are convinced with this. And now I finish the first topic. I move on to second topic, that is oxidative dehydrogenation of ethane to ethylene. So, to be honest, ethylene is the king of olefin market. It's the largest of olefin markets. So, it produces about more than 140 million tons per annum. So, normally olefins are produced different commercial process, the steam cracking and the FCC, and other one is catalytic dehydrogenation of paraffins. But all these processes have some disadvantages. So they are highly endothermic, they need high energy and high temperature input in the range of 700 to 1000 degrees. So extensive coke formation that leads to deactivation, and then that makes the process more expensive. So one good option is to introduce little oxygen in your reactant feed and to dehydrogenate. This is called oxidative dehydrogenation, which is an exothermic process and operates at low temperatures. When it operates at low temperatures and you have a presence of oxygen, so the paraffin, your alkane, will be easily activated at low temperatures. And presence of oxygen will also burn the coke which is deposited there, so that it will enhance the long-term stability. But this approach is still under developmental stage. It has not commercialized yet. It might take another decade or so. So if you look at the global demand and supply, so I compared here 1995 to 2030. So we are here now 2018, we are here now. So in 1995, the production of ethylene was 70 million metric tons, which is almost double last year. And then it's also expected to be 70 to 235, roughly 3.5 times by 2030. That clearly demonstrates the importance and demand for ethylene. The annual growth rate was 3%, and now it is expected to be 4%. So now, if you look at this ethylene consumption forecast across the globe, you can see Western Europe is almost saturated, more or less. United States and North America is the same. The highest consumption is expected in the region, Asia Pacific region. It is very clear. At the moment, in 2018 or 2017, we have reached 7.6 billion global population, of which 2.8 billion population located in India and China. India has 1.41 billion and China has 1.35 billion, more or less close. So more the people, more consumption. This is very clear. So if you look at the contribution of Asia Pacific region, it accounts to 35%, followed by North America and Middle East. And where does this 140 million ethylene go? To what products? So nearly 60% of ethylene produced goes towards polyethylene. So that is, you can't read, I think. This is a high density polyethylene, low density polyethylene, linear low density polyethylene, some of it goes to more than 60%, followed by ethylene oxide and then EDC. EDC in turn will convert into vinyl chloride, which also has a huge market. Roughly 35 million tons of vinyl chloride is produced every year. So we have used a variety of catalysts for the synthesis of ethylene from ethane, mainly vanadium-based catalysts, molybdenum-based catalysts, and also low temperature nickel niobium metal doped catalysts. So these are the results. So from the best case, we reached roughly 30% conversion, 35%, and the selectivity of more than 90%, which is good. This means the yield is over 30%. So 30% yield is not enough for commercial application. So the process is running, steam crackers running at 80% yields. So a long way to go. The next topic is benzene hydroxylation to phenol. This is a very challenging topic. In the gas phase up to now, the best yield of phenol achieved from benzene is less than 10%. So nobody could go beyond 10% yields. So about 10 million tons of phenol is produced worldwide. We use different geolite supported metal doped catalyst, and from the best case we reached nearly 27% yield at 33%, 34% conversion of benzene, which is the best result reported so far. We also submitted to patent manuscripts last year and before that. They are not published yet. So the last topic of part 1 is oxidative coupling of methane with toluene to form ethyl benzene and styrene. So one is almost inert methane and is highly reactive toluene. How do you couple them? Here we use methane as a source of methyl group. This is a part of natural gas utilization. So you need to go 500, 600 degrees centigrade minimum to activate this. At such temperature, this cannot survive. So you have to find a catalyst which can combine these two and produce these two. And the styrene, you know, roughly 30 million tons are produced, all huge large scale chemicals last year, and it goes to polystyrene, rubbers, resins and so on. So we have applied different variety of catalysts, and now at the moment we could reach conversion of toluene to 50 to 70%, and the yield of C8, these two is 120%. But there is only limited literature available on this. This is now very hot topic in scientific community, catalyst community. So now I move to second part, and I selected oxidation of toluene to benzyl acetate as a model reaction. I will show you why we selected this. In the first case, when I use gold nanoparticles, I will show you the small nanoparticles are better. The opposite is true in this case. We need bigger. We use here palladium catalyst, and we need bigger particles. Bigger particles are more active than smaller one. How it happens? I will show you a little later. So I will also first show the background, how we are motivated, what are the key issues that need to be considered to develop a catalyst. So what is acetylation? Acetylation is a process of converting alkyl group into ester group in presence of acetic acid and oxygen. If you don't have oxygen, it is simple acetylation in organic chemistry. So we are using oxygen also, that's what we call acetoxylation. So depending upon the reaction conditions and nature of catalyst you apply, the oxidation of toluene can be directed in 3 different ways. If we use strong uric acid, aluminum chloride, so there's just one molecule of toluene coupled with another one that leads to formation of bitolide. If we use strong oxidizing agents, potassium dichromate, permanganate and so on, then it goes ring oxidation that leads to formation of toluene acetate. But we want side chain oxidation. So for that, so our interest lies in the third direction, and to produce especially benzyl acetate, we don't want the second product, benzene diacetate. This is an over acetoxylated product, and this is only possible in liquid phase where the catalyst is in contact with your reactants for 2 hours, 3 hours, 10 hours. So in the gas phase, we are giving contact time of 1 to 1.5 seconds. So the product is removed, benzyl acetate, so we don't have a chance to undergo second hydrogen replacement with acetate group. So what is the commercial process for benzyl acetate? The commercial process of benzyl acetate involves multi-steps. We start from toluene, goes to benzyl chloride, and then benzyl alcohol, and then benzyl acetate. This is not very attractive. One is that, and second is that you use chlorine. Chlorine chemistry is not preferred nowadays from sustainable point of view. So our intention is to produce benzyl acetate in one step using palladium catalyst. Once you have benzyl acetate, it is also possible to go in the direction of benzyl alcohol by simple hydrolysis. The best thing would be to produce benzyl alcohol from toluene, which is very difficult. Not that easy, as I show in the paper. So coming to the commercial application, benzyl acetate is used in perfumery, food and chemical industries. It smells like a jasmine. When you have high yields, reaction running well, you are doing online. If You enter the lab, you smell the jasmine. So now, before going to show my results, I just show one slide on the state of the art on this particular reaction. The first example is liquid phase. So it is not our interest. We are doing in the gas phase. So here in the liquid phase, 100% conversion is reported, and the yield of benzene ester is 77%, but you have 23% of benzene diester, which is not desired. So if you look at this table, it's very clear that the conversion of toluene and the yield of benzene ester achieved is less than 20%. It's not huge. This means, therefore, there is an ample scope for further development. The first point. And second is, palladium is widely used. It's there everywhere. So, we have made efforts to develop catalysts, also using palladium and other composition. And we were able to reach more than 90% conversion and more than 70% yield of benzene ester, which is really good achievement. But we still have the problem of deactivation. So in subsequent efforts, by modifying the catalyst composition, we were also able to prevent the deactivation successfully. But we lost some activity. Doesn't matter. The activity is lost, but this is somewhat compensated by the enhanced selectivity. Here the selectivity is more than 95%. Here you have between 80 to 85. So, the catalyst preparation was palladium antimony TiO2. This is a well optimized catalyst. I will show you a little later why we select this composition. Why only this composition, why not other catalysts. I will show you a little later. But the preparation of this catalyst involves two steps. In the first step, we impregnate antimony, and in the second step, we impregnate palladium. And after impregnation, we know that palladium particle and palladium particle composition matters a lot for this reaction. We need bigger particles. In order to have bigger particles in the beginning itself, so we are given different thermal treatments, with calcination treatments. First we calcine at 300 degrees centigrade in air. There were no formation of bigger particles. Then we thought, okay, we will calcine at high temperatures, 600 degrees in air, one oxidizing, and then we want to see inert, and we want to see reducing atmosphere at 600 degrees centigrade, and see how the particle morphology and particle composition, particle size, shape changes with this thermal treatment. And everyone has clear influence. We will see it later. But when we calcine hydrogen, we have seen the formation of intermetallic compounds between palladium and antimony. And these intermetallics are not actually selective. So I am not going to show any results from this reduced atmospheric calcination catalyst. So I just compare now these three. 10 degrees in air, 600 degrees air, 600 degrees air. Now I will show you the key issues is that why palladium and why antimony. In the beginning of our approach, we tried pure TiO2, which is almost inactive as expected, and this is monometallic antimony. I don't know whether you are able to read this. Antimony and titanium, only antimony, monometallic. Also more or less inactive. You can see this, the red column, the conversion of this toluene, and the green one is the yield of benzene ester. So when we use only palladium, this is only pure TiO2, monometallic antimony and titanium, monometallic palladium and titanium, and then combined palladium, antimony and titanium. So if you look at here, when I use pure palladium, pure in the sense monometallic, 5% palladium and titanium, the reaction is going in wrong direction. So the violet one is the conversion of acetic acid, and the blue one is yield of carbon dioxide. We don't want to have carbon dioxide, we're simply burning acetic acid. We want to have benzene ester. But when I combine palladium and antimony, you can see the conversion of 2% increases to more than 35%, which is amazing. And the yield of benzene ester also increased nearly 30%. Quite surprisingly, astonishingly, the yield of COX drastically reduced from 50% to 5%. This is what we want. So, therefore, we selected palladium antimony composition. Then you may ask, why only antimony? Why not other promoters? So we have tried a variety of promoters. I can show you here. So of course we are convinced now this palladium antimony combination is essential. So when we changed other promoters, antimony, bismuth, tin, copper, and so on, you can again see the red column and blue one. So the conversion is highest in case of antimony compared to other promoters. This means antimony is necessary. Then you ask, why titanium? Why not other supports? The selection is purely based on performance. So if you compare titania, silica, zircon and alumina, you can see the highest conversion is achieved in case of titania and high selectivity compared to all other supports. So what we learned from this study, combination of palladium antimony is essential. Antimony is the best promoter and titanium is the best support. Now it's convincing that we need palladium antimony and titanium, but we don't know how much actual concentration of content of palladium we need, how much antimony we need. So what is the right optimum? In order to find out this, we prepared two separate series of catalysts. In the first case, we kept antimony constant and changed palladium over a wide range, and we checked which amount of palladium is necessary. And in the second case, we fixed this optimized palladium content and we changed the antimony. This I am going to show in the next slide. So this is the effect of palladium loading, 0.5 to 28% on the conversion activity and selectivity. If you look at this, the conversion is increasing rapidly up to 10% and then increasing slowly beyond 10%. So in fact, 20% palladium is the best one, and the selectivity is independent of conversion. This means the benzyl acetate is quite stable product. It is not undergoing any further reactions, conjugative reactions. But 20%. 5 minutes. 5 minutes. I'm not reached off. I'm not even reached off. Okay, then the yield 20% more expensive, then we took 10% as an optimum. And then we kept the 10% constant and then changed the antimony loading. And we reached 8% antimony is the best one. So we fixed this composition, 10% palladium and 8% antimony. So I've shown you that palladium antimony contents reveal strong influence. We could reach more than 9% conversion and more than 85% selectivity of benzyl acetate. So now I will show you the change in particle size and their influence on the performance. Let us start with the first one, the time and behavior of the catalyst. The catalyst exhibited very low initial activity, nearly zero, start from zero, and then increasing continuously until 10 or 11 hours, remains stable for 2 to 3 hours, not much, and then going down. It undergoes deactivation. What is the reason for this increase in conversion, and what is the reason for this deactivation? So the reason for increase in yield is increase in palladium particle size. You may wonder, how come this? I will try to convince you little in a moment. And the deactivation is due to coke. So what we have done, we have collected a sample at different stages of reaction. The fresh one, the maximum active one at this stage, and the half active one, maximum active one, deactivated one, and regenerated one. And we check the particle size. We stop the reaction after 5 hours and immediately analyze by 10. We stop the reaction at 10 hours, immediately analyzed. So now you will see, I request your kind attention to watch carefully, because here we are going to see 3 changes. Change in palladium particle size, change in the conversion, change in the coke deposition. So the fresh catalyst, very small palladium particles, you can't see. And coke is also not there, just air calcium one. If you go after 6 hours, sample from here, the conversion increased from here to 35%, and the coke is also increased. And the palladium particles begin to grow. If you look at the electron micrographs, the maximum active sample and the deactivated one, the coke is further increased from 1.2 to 2.3, and the conversion increased 35% to 68% after 11 hours. The particles also become 50 to 100 nanometers. Even though there is 2% coke, the catalyst is still able to show the maximum activity. This means the 2% coke is tolerance coke. It is not able to block all your palladium sites. It can sustain 2% coke. But if you go further, if you have 4 or 6% coke, the catalyst is undergoing deactivation. So then we are regenerated the catalyst. When you regenerate catalyst, the coke is removed, the particle size remains same or less same. This means regeneration has no influence on the palladium particle size, but can only remove the coke. But we are not reached to zero. There is still 1.7% coke at this attempt. And we have seen here already 2% coke has not that influence. So catalyst can still work. So the problem here is the long induction period. One has to wait 11 hours, which is disappointing. One is not, you are not happy to wait. So our next aim is to reduce this induction period from 11 hours to 0 if possible, otherwise to reduce to the possible extent, maximum possible extent, and then improve this long-term stability. This is the target. So this is the story about the catalyst calcium 300. Now let's have a look at the catalyst calcium 600 in air. So if you compare the previous one, the stability increased nearly 10 hours, from 2 hours to 10 hours. Some improvement. And then it also undergoing deactivation. And again we collect the sample at different stages. The fresh one, even after calcium at 600 degrees C, you still have small palladium particles. The 600 degrees calcination has not made any growth in the palladium particle size. So, but when you reach the maximum activity, the catalysts have grown to 30 to 50 nanometers. And the particles shapes are different. You don't have uniform. We want to have uniform size, but you have cuboid, triangular, spherical, different shapes. The morphology is not the uniform. And if you look at this deactivated one, if you not only look at the particle size, but also look at the particle composition. Sometimes antimony enriched particles, sometimes palladium enriched particles. This is not homogeneous distribution. This is also another reason why 600 degrees calcination has not brought to the extent we want. There is some improvement. Now this also prompted us to improve the growth of palladium particles to the maximum extent, not the maximum 30 to 50 nanometers. So then let's compare with helium one. So when you calcine helium, the long-term stability is much more improved. The induction period remains same like air one at 600, but somewhat better than the first one. So on the whole, helium is the best. Again, if you look at the particle size, when we calcine the catalyst in helium at 600 degrees centigrade, we have seen the formation of the biggest particles. Too much, huge. Quite surprising thing is that these bigger particles undergo kind of reconstruction or tuning itself under the influence of reaction conditions and the reactant feed mixture, and it forms again the particles of critical size 30 to 50 nanometers, which is really surprising. And if you look at the spent ones here, and spent in the sense of 30 hours, you still have bigger particles, and with the composition of palladium to antimony 5. So where does this antimony come? This means in the process of reaction, during the course of reaction, certain amount of small amounts of antimony is incorporated into the palladium lattice, which is essential. So comparing all these three, helium is the best one, but I have shown you until 30 hours. What happens if you go beyond 35 hours, 50 hours, 40 hours? So we can see we have a deactivation.
Done.
So also the helium calcium 1 undergoes deactivation. And what is the reason for deactivation?
Done.
What? Okay. So this due to coke formation, we estimate the coke as a function of time. The coke is increasing with increasing the reaction time. And then when the deactivation is inevitable, so you can't avoid it, you have to look for the regeneration procedure. So based on this, we have done the spent sample where we have coke. We have done by thermal analysis, TG, thermographic analysis, where you can see the coke is removed in the temperature range from 200 to 400 degrees centigrade. So, and the coke is going in 2 steps. So that means this gives hints that you have 2 types of carbon species. One is carboxyl group, one is on the surface, and the other carbon is incorporated in palladium lattice. But anyway, so we have to select the temperature for regeneration between 250 to 400. So we try to regenerate sample at 250. We are able to regenerate, but the regenerate catalyst is undergoing faster, rapid deactivation. This prompted us to go a little higher to 300, is somewhat better. And then we thought, okay, maybe if you go to 350, it might be much better than this. Quite surprisingly, we are not able to regenerate 350. 300. 300 you can regenerate, but 350 you can't. So something different chemistry is going on. Then we also gone beyond the 350. We went to 400, same situation. Why we are able to regenerate the catalyst at 250 and 300? Why we are not able to regenerate the catalyst at 350 and 400? So what kind of chemistry going on? So this remained big question mark. So we want to explore why we are not able to regenerate. What is happening in the catalyst structure? So for that we estimated first the catalyst composition. These are 6 hours the maximum active one. We have 2 palladium species, metallic palladium and oxidized palladium. They are existing in roughly 1 to 1. And in the spent catalyst where it is deactivated, this palladium oxide is completely reduced to palladium metal. So we need both palladium oxide and palladium metal. So as long as palladium oxide is not there, the activity is lost. This is one hint. When we calcinate 300, you are able to restore palladium oxide, the blue one, but you are not able to restore palladium oxide at 350 case. So we run this, then we regenerate again second time, second regeneration. We are still able to regenerate only at 300 but not at 350. And then we estimated the actual concentration of palladium and palladium oxide on the surface. You look at this diagram. So in the maximum catalyst you have roughly 1 to 1, both palladium and palladium oxide, and the spent catalyst only palladium, and the regenerated 300 you have both you have, and in the regenerated 1 at 350 you don't have it. This is the story of palladium. What happens with the antimony? We also have antimony. So what is happening with this? If you look at the antimony, fresh one you have antimony, considered high amounts, and in the maximum active one, some of the antimony is pushed to the migrated to the surface, and in the spent one also you have antimony, but when you regenerate 300 you could bring back antimony, when you regenerate 350 there is a loss of antimony. This is another hint. So this is the story of palladium, the story of antimony, and what is the story of coke? If you look at the coke on the surface, we are talking about XPS. So you have 2 types of coke, aliphatic and a carboxyl from acetic acid. So this is high in case of deactivated one, and when you regenerate, you can remove this, you consider extent, but when you regenerate at 350, so the coke is increasing instead of decreasing. This means the carbon species are migrating from bulk to the surface. On the whole, we can conclude that the loss of palladium oxide, loss of antimony, and the migration of carbon species are collectively responsible for the by 350 you are not able to regenerate. So now I just covered 3 slides. Okay, very fast.
We don't have time. We don't have time. I think you have to repeat the conclusion, please.
Okay, I will go here. I will do 1 slide. So we just shown titanium anatase and rutile. Then not only the coke amount of coke deposition differs, the nature of coke also matters a lot. There is a huge difference in the nature of coke. When we deactivate, anatase is deactivating catalyst, rutile supported catalyst is non-deactivating catalyst. In this case, catalyst, there is a carbon deposition directly on the palladium particle. If you estimate the carbon layer thickness, it accounts to 1.69 nanometers. And if you see non-deactivating catalyst, the carbon deposition is preferentially going to the rutile crystals on the surface, on the support, not blocking palladium sites. This is one reason why rutile is better than anatase. And also, if you look at the carbon layer thickness, 1.3 nanometers against 1.69 in case of this. So this also matters. So some isotopic experiments, but I will skip this. So now I have shown the possibility of forming adipic acid in one step from cyclohexane using gold nanoparticles, and oxidative dehydrogenation of ethane more likely compete with steam crackers in the near future, and palladium size and its composition has shown remarkable influence on the activity and selectivity. Deactivation of this catalyst is due to coal, and mainly due to, I skipped this palladium delta minus formation species, and surface composition and distribution of different palladium species on the surface play a key role on the active selectivity. Lattice oxygen takes part in the formation of water, and acetic acid is the main prime source of coke and carbon dioxide formation. So I would like to thank our group members, and also I would like to thank you all for your kind attention. Now I am looking forward to your questions or comments. Now it's your turn. Thank you all.
Thank you. Thank you very much for your impressive lecture. I would say we don't have enough time for just one question. Yeah? Any other questions?
Okay, move.
I have only one question regarding the oxidative dehydrogenation methane. You presented something using little amount of oxygen for the improving the yield, which is actually only 35. The loss of yield due to the oxidation of the product by the oxygens that they are using. Did you thought to change, instead of using oxygen as an oxidizing agent, use the lattice of the catalyst as an oxidizing agent?
We have used the lattice one. We also used admixture of carbon dioxide as a soft oxide. We also done both. So when we add carbon dioxide, which is a small amount of this thing, you little bit enhance the selectivity of this. If you use lattice, you may run 1 hour, 2 hours, and then it goes. That's actually finished, and it carries on towards deactivation much faster. But we are not using 1 to 0.5. The stoichiometric oxygen we are using. If you use more oxygen, the ethylene will be easily activated and it will burn its X. So you have to find a balance of the oxygen concentration versus ethane activation.
Okay, thank you. We'll continue our discussion later.
But I started level 45.
Yeah, it's 40. You got 45. You got 45 minutes.
اتفضل.
Level 30 session, it started level 45 and 45 12 30.
We're happy. We're happy too.
Yeah, but okay. 40 minutes and not finished yet. I still have 10 minutes. I still have 10 minutes.
So do you have any question more for?
Yeah, please. Okay, thank you.
Okay, thank you very much for your kind presentation.